All right, welcome to Unit 5 in the wonderful world of graphing quadratic equations. First question asks us to complete a table of values, plot the points on the graph, and draw the parabola. So here's our equation, y equals x squared. So we set up a table of values, we plug in our x values to get our y values until we have a series of coordinates. Then we plot them on the Cartesian graph, connect them, and we have a shape that's a bit different from something we've seen before. It looks like a cone, and we refer to this shape as a parabola. And you'll notice that this specific parabola has a lower vertex of 0, 0. The vertex is the point at which the curve changes and heads back into another direction. So our equation is y equals x squared. You'll notice that the x squared has a positive coefficient, in this case 1. Okay. When it's like this, take note of which direction the parabola is pointing, or opens up. Here are the coordinates plotted in, same parabola. Notice again that the vertex is 0, 0, and it crosses the y-axis at a point of 0. Here is a second equation, y equals negative x squared plus 8. Once again, we're asked to complete a table of values. So we'll put in all of our coordinates. And then plot them on the Cartesian plane. Connect the points. And we have another parabola. This one opens up down, however. And the reason for this is that if you look at the equation, it says y equals negative x squared. The coefficient of the x squared is a negative number. And when this happens, the parabola opens up downward. Take note of the y-intercept, 0, 8, and compare that to the equation y equals negative x squared plus 8. You'll start to see patterns and start to recognize what these various numbers mean and how they relate to how they show up on the graph. Here we have another equation, y equals x squared minus 2x minus 8. You'll notice that the x squared term comes first, followed by the negative 2x, followed by the negative 8. This particular pattern is what's known as standard form, where the exponent comes first, the term with a single x comes second, and the term without any variable at all comes third. So exponent first, x second, number without a variable third, standard form. Okay, once again, we're asked to complete a table of values, which I'll do quickly here. There we have a whole series of points that we can plot on the graph. And when we join the points, we see that we get another parabola. Notice how this one is facing up again, and that's because the coefficient of our x squared term is positive. Take note of how the y-intercept compares to our equation, and how our x-intercept compares to the equation. We'll start to recognize patterns, as I said before, between x and y intercepts and our trinomial equations or quadratic equations. Okay, just to review some of the initial observations. As said before, when the coefficient of the x squared term is positive, the graph will open up. And when it's negative, it'll cause the graph to open downwards. The coefficient of the x squared term also has another effect. The bigger the number in front of the x squared term, or the bigger the coefficient of the x squared term, the steeper the graph will be. And you'll notice that the purple line that has a y equals x squared equation, the coefficient is 1, and it is of a certain steepness. Then the green graph has a coefficient of 2, and you'll notice that the graph becomes a little bit steeper. And the red graph has a coefficient of 3, and you'll see that the graph is a bit steeper as well. Now there's also a coefficient in front of the x term that has an effect on the graph. And as if you change these values, as in changing it from 1 to 2 to 4, you'll see that it moves the graph left and right. And the constant value, the term with no variable, as we change that, it moves the graph up and down. So x squared plus 4 is represented by the green graph. The red graph, x squared plus 2, its vertex is a little bit lower. And the purple graph is negative 3, and you'll see that its vertex is even lower. Okay, once again, reviewing the effect of changing the coefficient on the x squared term. Now, when we write these equations in standard terms, as I said before, we have an x squared term, we have an x term, and we have a constant. We'll often refer to the coefficient in front of the x squared term as a, and the coefficient in front of the x term as b. And the constant value without any variable we'll refer to as c. So in this particular equation, y equals x squared, we have an a value, or a coefficient of the x squared. And in this particular example, the coefficient is 1. So we say that a has a value of 1. And our graph looks like this. So y equals x squared is a very symmetrical parabola or very symmetrical graph that mirrors the x-axis. So just take note of what the graph y equals x squared looks like. Now, if we change the coefficient to -1, or make a negative value, once again, you can see how now the graph opens up downwards. It flips the graph. Here is our y equals x squared graph again. A has a coefficient of 1. And just take a moment to take a view of how steep the graph is. Now we're going to change the coefficient to 2. And you'll see that the sides of the graph are a little bit steeper. In this graph, we'll change the coefficient of the x squared term, or the value of a, to 4. And it is a bit steeper again. We can also make the coefficient less than 1. In this terms, we made it a little bit smaller. We made it 1/2 x squared. And you'll see that it makes the graph a little bit fatter, for lack of a better term, or just less steep. Decrease the coefficient of x, or decrease the value of a little bit more to 1/4, and you can see that the graph is spread out even more. There are a number of excellent sites with animations that allow us to manipulate these values of a, b, and c. So one of these, let's explore that. So here we can adjust the values of a, b, and c. Right now we have an equation of y equals x squared. So a has a value of 1. We can adjust the a value down here. If we make it 2, you can see how it gets steeper. Up to 4, even steeper, and we can just move that all the way up to 10. Or we could reduce the size of a to a fraction. It's 0.5, or 1/2. There's 1/5. And notice that when we take it to 0, it becomes flat. Okay, so we'll move the value back up to 1 again of a, and let's start moving or adjusting the value of b a little bit. So notice, as I move this slider a little bit, the value of x, the coefficient of the x term, changes here. So I can move this up to 3. And notice what happens to the graph. It moves a little bit left and down, or right. So this gives you a little idea of what adjusting the values of the x term, the coefficient of the x term, is. And lastly, we have the constant, the c. And if we just move this a little bit, I'll put this constant value, or the c value, up to 3, and you notice that it moves the vertex of the graph up 3 points. I can do the same with negative values. Once again, it just lets you visualize the effect of changing some of these values. There's another site here. Let's have a look at that. So we're using, for the time being, we're interested in something called standard form. So we'll click on that. And here we have just a slightly different way of changing these values. Instead of using the slider, we just click the buttons, but it basically does the same thing as the previous example. Change the values. Change the constant. Again, another excellent tool just to explore the effects of manipulating these various values.